This kind of, this is very heuristic. I mean, because we are actually not deriving anything. What we're doing is that we are coming up with a new physics. So, what about the classical limit? So whenever you come up with new physics, in some limit, it must always agree with the old physics that is tested and tried, right? So you've got new physics, and there will be some limit of some parameter where you'll get old physics. If your new physics in that limit does not agree with the old physics, that means that your new physics is not a correct description of the world. It may be mathematically consistent, it may be interesting, but it may not be the correct description of our world. Can someone give me an example of this? Of where, we actually do have a successful physical theory, which in some limit does give us an older successful theory.
Special relativity.
Right, special relativity, gives us at small velocities, at small speeds compared to speed of light, Newtonian mechanics. Similarly, if you look at Einstein theory of relativity, for small curvatures, you actually do get Newtonian gravity, okay? You can derive the Newtonian potential, for example. So similarly, we get classical physics from quantum mechanics by taking h bar to 0. This is the naive limit. So it would be interesting to see what this thing gives us in the naive limit. So if I look at e to this sum where we are all the paths, I by h bar s, if I look at it, now, if you now take, say, one of these paths, suppose you take this path, and you look at another path which is slightly different from this path, say a neighboring path. Okay, so let's take a neighboring path. I'm exaggerating it, but let's let it be slow. Now the thing is that because we are taking h to be 0, we are taking h to be 0, any small variation in s will get magnified because the factor in front of s is very, very large, right? In this limit, a small variation of s will result in a large difference in this whole thing because the constant in front of s is very large. So that means that for a small variation of the path, because s is going to change, this phase factor will change in some random way. So when we take the sum over all these paths, because these phase factors are changing in random way, they will tend to cancel out. So in the h goes to 0 limit, most of the path will not contribute. Because they'll tend to cancel each other. But there's one special path for which if you change the path slightly, the change of the action will be 0. That is the classical path. That is the path that the classical particle takes, okay? So if this is my initial position and this is my final position, and this is, say, the classical path, right? So if I take little variation of the classical path, what will happen is that the change in the action will be 0. So the change, the contribution to this sum from this small tube of paths around the classical paths. So this is the classical path of the particle. Okay. So all these paths which are nearby, they will contribute, they will interfere constructively. So in this path integral, the contribution in the age goes to the 0 limit will come from essentially the classical path and its neighbors, which means that in the classical limit, we do get classical mechanics from this crazy path integral theory. So it passes this very important test. Okay? Is that clear? Shujosh?
Yes, sir.